7, 6, 5, 4, 3, 2, 1.
Ten, nine, 8, 7, 6, 5, 4, 3, 2, 1, 0.
I'm muted, I'm unmuted now. There we go. I'm really bad at that. Messed that up a lot. All right, hello everyone. Welcome to the stream. Welcome to another edition of Cracking the Coding Interview with Rust. We are learning Rust-lang, learning programming stuff. We're having a good time, enjoying the stream. Welcome back if you have previously joined us, and welcome for the first time if you are a new viewer. So since I last streamed, I published a blog post that got a little bit of traction, got posted to Hacker Noon and was on Reddit, and I think it was very briefly on the front page of Hacker News for like 3 minutes until the algorithms decided it was unworthy. But anyway, if you found me from that blog post, then welcome. Thanks for reading it. I hope you liked it. I hope you didn't hate it. I suppose if you decided to tune in now, then it probably means that you liked it, so that's good. All right, what are we doing here? So if you're brand new, if you've never heard of any of this or me or whatever before, we're going through the book. This book here, it's called Cracking the Coding Interview, written by Gail Lackman McDowell, and this book contains a bunch of interview problems, which are it's basically algorithms practice. It's all very algorithmically focused. The types of problems that are in this book are not really very practical, adjusting the camera there, but they are definitely I would say the status quo type of problem that you're going to have to face probably at some point if you ever want to get a job as a software engineer, developer, programmer, whatever. Most interviews are still going to be in the style of those in this book, unfortunately. So it's good practice. It's also fun just to do the problems, I think, personally. Not in an interview. I hate doing these problems in an interview, but doing them just for fun is fun. It's also a good way to learn programming or learn a new language. That's why I started doing this, because I really wanted to learn Rust properly, and I'd never really had a like a good way to do it before. I'd made like some small projects here and there, but nothing significant, and I thought this would be a good way to force myself to really learn it properly. All right, so here we are. I want to do something slightly different this week, and I want to begin by doing a little review of what's happened in Rust this week. Before I do that, by the way, if you want to check out the code that I'm writing, it's up on GitHub. You can just go to my GitHub profile / cracking the coding interview Rust. I should share my screen, just as you see here on my screen. Let me fix this chat window. There we go. Make sure those pixels are lined up. Good enough. I'll take it. Okay, let's close OBS here. So yeah, let's start off by doing a little review of what's happened in Rust in the past week. So there is a project which is called This Week in Rust, and this is a a weekly, I guess you can call it a blog post or whatever. I guess there are 277 of them. If you want to keep up with what's going on in Rust, this is a good place to start. It's a project on GitHub. Anyone can contribute and just submit a PR. If you want to find it, you can just go to thisweekinrust.org, and there it is. So this is a cool thing to read. Now I'm going to jump into some of the things I saw this week that I thought were pretty interesting. And I want to start off with this micro profile, which is a really cool thing that I saw yesterday. It is a profiling tool for Rust, which is super useful. I have not really been in a situation where I need to do any kind of profiling, but if, now that I think about it, if I had, in fact, it's something I don't think I mentioned in that blog post I published, but if I had to do profiling in Rust, of course, now that I think about it, I honestly don't even know well, aside from this tool here, I don't even know where I would start trying to profile things in Rust. Other languages, of course, have profiling tools. I've used Valgrind a lot, which is super useful. I've used other things as well, dtrace, strace. I guess strace isn't so much a profiling tool, but anyway, regardless, when you're really serious into building stuff, eventually you're going to hit the point where you need to figure out why certain things are taking as long as they are, and there's no better way than using a proper profiling tool and instrumenting your code. So those are, I guess, two different but related things. Usually when it comes to instrumentation for production services, for example, you would use some sort of metrics library that's writing data out to statsd or something of that nature. Which is slightly different from profile, a profiling tool normally, where that's something where you would be testing the code on your laptop and maybe using unit tests or whatever, some sort of controlled environment where you are measuring certain parts of the code to try and figure out where time is being spent and what you can improve and so on. So anyway, this is pretty cool. It looks like it has a type of flame graph going on here, if you're familiar with flame graphs. Yeah, here's a blog post by Brenden Gregg, fellow first name sharer of mine, well, off by one character, but anyway, these are flame graphs, which is just a way of visualizing what, where time is being spent in your code. It's a pretty cool visualization, and it gives you a really quick way to figure out where is the time going when you run something and it's super slow and you can't figure out why. Really, the best thing to do is to measure rather than trying to guess. if you guess, you're probably going to be wrong, or you might be half right, and so on. So anyway, as I think Donald Knuth, I don't even know how to pronounce his name properly. I think he's the one credited with the quote of saying premature optimization is the root of evil, or all evil, or something like that. Yeah. I guess he said this in a paper. Premature optimization is the root of all evil. Anyway, don't bother optimizing your code until it really makes sense to do so, and that it usually doesn't make sense until it's done and you've found all the bugs and it's working, and then you can go back in and start making changes. It's really pointless to do it ahead of time, because chances are the first time you run it, it's not even going to work correctly. It might even appear to work correctly, but until you've actually run it for a little while and you know, validated that it works, there's a good chance that it doesn't actually work. At least that has always been my experience. Even when you make the compiler happy, there are often logic bugs that don't appear until you start trying to run things. And even having unit tests is often not sufficient. So anyway, all right, this is one thing. It's called micro profile. This is on the Rust Reddit group, which is pretty good actually. I think a lot of subreddits are pretty crap these days. Most of Reddit is kind of crap these days, if I'm honest. But there are still a lot of like smaller subreddits that haven't been completely overrun by garbage, which is nice. And the Rust subreddit is still pretty good in my experience. So anyway, check it out. There's some good threads, by the way, in the Rust subreddit. There's like this weekly one. There's like this "What are you working on?" thread, which is pretty cool. You can get an idea of like what other people are up to, and that's neat. So check it out. All right. So the other thing I want to talk about that popped up this week is this tutorial on hardware debugging using Jtag. So if you've ever done any kind of like embedded programming, although honestly calling Raspberry Pi embedded is a bit of a stretch. It's basically, I mean, the way most people use Raspberry Pis is not quite what I would call embedded. You've got like a full Linux kernel and stuff on there, which is like, I wouldn't call that embedded programming. But this particular blog post is talking about like, okay, what if you want to like actually maybe even like write your own kernel or something, do like actual embedded programming. You could use the Raspberry Pi for that. It's open hardware, and this is a tutorial on just how to like get started doing hardware debugging, which is really cool. And if you've never tried to do this, like never tried to do embedded programming or like lower level stuff like this, then it's really fun. There's a lot to learn. It is something where you like, it involves physical hardware, which is definitely different. You have to actually like have like a physical space where you can set this stuff up. You gotta like connect cables and wires, and you might even have to learn how to solder if you don't already know how. It's not hard, you just gotta be careful not to burn yourself. That's the main thing, which I've done many times. But anyway, this is pretty cool. So if you're curious, hell, if you want to like try to write your own kernel in Rust or something, or there's like, I've seen there's like a few write your own OS in Rust things out there, which is really cool. I personally haven't like looked into any of that. I mean, I've seen it, but I haven't like tried. Although that would definitely be a cool project. Maybe someday. I feel like I have more than enough projects in my life at this point. My challenge is figuring out like which one to work on this day, and whether or not I want to go down a new rabbit hole every time I come across a rabbit hole. But anyway, check this out. if you've never done embedded programming, maybe give this a shot. You can buy a Raspberry Pi for like, you can buy a kit for like 30 bucks off Amazon, depending on where you are. If you're spending more than about $30 on a Raspberry Pi, then something has gone wrong and you need to figure out what's happening, why that's happening. Shouldn't be happening. I think you can get like a whole kit with power supply, SD card, and everything for like 50 or less. Let's just do a search here on Amazon. Yeah, $54 for, I don't think this has the SD card. Okay, everything except for the SD card. This has a case. I think these heat sinks are kind of silly, but you know, they put it, oh wait, maybe, oh yeah, here's like a thing Amazon's pitching me here, which is the kit plus an SD card for $62. That's US, of course. I think you can probably get it a little cheaper, actually. Oh look, here, this one, here we go. This one includes an SD card, 8 gigabytes. Oh, but I think there's no power supply. I don't know. Anyway, it's pretty cheap. Probably not going to break the bank, and it's a fun way to learn lower level stuff. You can build a lot of cool things with Raspberry Pis. I have like several of them, just kind of like all over the place. And if you want a little more juice, then you can look into like the Intel Nook or whatever. I don't know how that's supposed to be pronounced, but that's what I say. These are like full Intel PCs, basically. I don't think they have like GPIO pins or anything on them, but I have a couple of these as well that I use for various things. Like I have my own file server and stuff like that. Anyway, okay, moving on. Let's get to the project. Cracking the coding interview with Rust. Let's see, where are we? I should check that my sound is actually working. Make sure that it sounds. I don't think. Yep, there we go. I can hear my sound of my own voice, which is really unpleasant. So last week we got into chapter 4, which is trees and graphs. And I think, how far did we get? I'm gonna have to go look at the code because I don't remember. We got to chapter 4, problem 3. Problem 3 was list of depths. Got it. So we are moving on to chapter 4. Problem 4, chapter 4, problem 4. Problem 4 is called check balanced. And I can already guess what that means. I think it is about checking whether the tree is balanced or not. Duh. Okay, there we go. Check balanced. Implement a function to check if a binary tree is balanced. For the purpose of this question, a balanced tree is defined to be a tree such that the heights of the two subtrees of any node never differ by more than 1. Okay. Very good. So this is a variation of the last problem, which I think was list of depths or something. Anyway, so this sounds pretty straightforward to me. I think that I will be able to do this fairly quickly. Let's see. List of depths. I thought that I had implemented something to count. Oh, I see. Okay. So list of depths returns. Yeah, got it. Got it. Okay. So let's copy this. Problem 3. Paste that. We're on to problem 4. So problem 4 is called check balanced. Okay. Now to do this, I need to create both a balanced and an unbalanced tree, right? So here I only need this height guy, right? And max height. I'm just gonna delete this list of depths thing because I'm not going to use that. I don't need it. And I can't remember. I know that I had implemented at some point an algorithm to balance the tree, but I don't think that's in this code. I definitely don't want that. I want to, in order to test this, I need to be able to create an unbalanced tree. So, okay, it's only been a week, but I like completely forget everything about this code, pretty much. Let's insert, add vector. Huh, cool, okay. Is it all? I feel like a lot of this code is probably not being used. Height, list of depths. Let's get rid of that. Let's get rid of this, get rid of this, get rid of this. Add vector, I'm gonna keep that. Cargo test. Oh dear, forgot to switch my screen again. I do that way too much. It's really hard to like focus on what I'm doing and pay attention to the stream at the same time. Yes, I am aware. Is it Jonas or Jonas? I used to have a roommate. His name was Jonas. Jonas. I never really could pronounce it correctly. He was from Germany. Although your last name suggests maybe you are not from Germany. But yes, thank you for mentioning it. And welcome to the stream. Okay, so check balanced. Let me make sure this compiles. That is so weird that it compiles. I'm always surprised when my code compiles. Comes as a shock to me. Second way, got it. Oh, welcome. Okay, so here we have a tree, add vector. I need to remember what add vector does because I want to know if it's going to create a balanced tree or not. Yes, okay. So add vector is going to make this balanced, which is fine. I can use add vector to generate a balanced tree, and then to make an imbalanced tree, I can use, I presume, insert. Yes, okay. Cool. So just to test that, let me make sure that this is, let's call this one, whoops. Let's call this one balanced binary tree. Okay, this is balanced. And then let's make an imbalanced binary tree, which is going to be nearly the same thing, but imbalanced. I don't think RLS is working. Again, something's not working. Maybe it is working. I don't know. Okay, then for I in array, imbalance binary tree, insert I. There we go. Okay, then remove this guy, and this should fail now. Sweet. That is perfectly imbalanced. That is as imbalanced as you can possibly get. Perfect. Okay, and then we will add a new function here, check balanced. This one's going to return false. And then up here, check balanced. This should return true. Missing semicolon. All right, method not found. Perfect. So check balance is going to look a lot like this height calculation. So I'm literally just going to copy and paste those, but the return type will be different. So check balance is going to return a Boolean. Okay, and then here I just say if let blah blah blah, else false. Change this to that. That should be it. I can also simplify this code. This doesn't, I don't know why I wrote it this way. It doesn't need to be like that. It can just be like if else, else, 0. That is a little cleaner, more succinct. Okay. And then implementing this is really simple. So let's change these. So in this case, rather than keeping track of the maximum height, we want the height of the left and the height of the right. So we're gonna have left height equals 0, and then right height equals 0. Okay, and then delete this, delete this. Wait a minute. Might be making a mistake here. So the height, oh yeah, so I actually need to use, this other method. Let me just back up here. Okay, yeah, this is fine. So here I will say, no, I should do this differently. So I want the algorithm to stop early. Like as soon as the height differs by more than 1, I can stop searching, and I can just say no more. And yeah, I can, let me just copy this code and put it back over here, but change this. Let me think about this a little more for a second. So can this return a Boolean? Can this return a Boolean the way it is? I think I either need to add an additional function. So if I want to calculate the size recursively, like I did with this height inner, then the function should return the size. But if I want this to return a Boolean, then I either need to use an additional function or do something else differently. This should just be 1. There we go. So yeah, let me do it this way. Let's go check balanced. This is not necessarily going to be optimal, but I think it'll be correct. So left height equals 0. Equals 0. Okay. So the left height is going to be basically just a 1 here. And then right height one, and then I will return the absolute value. How do I do absolute value in Rust? Okay, so it'll be left height minus right height dot absolute value is less than or equal to 1. I don't need return. That should be it. Left, right. This should not be check balance. I'm going to use this height inner to actually calculate the height. And then change this. I don't need this height argument. That should be it, I think. Oh, this should be true, actually. If there's no no method, absolute value. Okay, so this needs to be as I32. Or I think I need to convert these to integers first, like that. I64, because I think U size is probably going to be 64 bits. Why does it not like my check balanced? Oh. Rust doesn't let you overload function names, at least not now, which is kind of annoying, honestly, but this is what it is. Boom! There it is. We're done. All right, that's problem 4. That's pretty straightforward. Git add problem 4. check that in. Push that to GitHub. How many problems are there? Good question. There are 189 problems in the book, according to what it says right there. 189 problems. I have done, yeah, and a lot of them are pretty easy. Like some of them, some of them I have gotten through very quickly. However, other ones have taken a very long time, like hours. So I've done 27, right? Excluding this line, it's 27 problems. So I've got a long way to go, but yeah, whatever. This last one took, I don't know how much I spent on this, like 20 minutes or something. It was pretty quick. Doing it in Rust definitely makes it, I think, a little harder to do them quickly. Oh, my build's gonna fail because I don't call this check balanced here. I need to call that. Whoops. So that Clippy passes. There we go. Let me fix that. Let me run Clippy here. There we go. Push that up. Yeah, it's gonna take me a long time to actually get through all of these, assuming I stick with it. I might just give up after some point. I'll try not to do that, but it's possible I may do that. I usually have a pretty good track record of not quitting, not giving up. So we'll see. Anyway, okay, on to the next problem. I was sharing my wrong screen again. Jeez, super bad about that. I wasn't doing anything interesting anyway. All right, validate BST. Oh, this one's super simple. Validate BST. Implement a function. Let me just make sure I'm showing this. Validate BST. Come on. Implement a function to check if a binary tree is a search tree. Okay. This is not that different from the last problem, but it's slightly different. So how do you validate a binary search tree? It's very simple. Binary search tree really only has one rule, which is that everything to one side needs to be less than or equal to the current node, and everything to the other side needs to be greater than or equal to the current node. That's it. So let's just put that into the code. Let's copy problem 4, paste problem 5. Here we are. Check. So let's get rid of check balanced and change this to check is BST. All right. So right now this is a binary search tree. When I do an insert, it's doing a I believe, yeah, this is a binary search tree. Like this code right here is basically checking here if node, if this value, the data here, is less than this value, then put it on the left. Otherwise, put it on the right. That's it. Very, very simple. So to break this, I'm going to have to manually insert some data that is not in the right place, which will be pretty easy. So, okay. And then to check that it's a properly balanced, or sorry, to check that it's a proper binary search tree, I'm going to, again, I'm going to reuse this code. I'm not going to use this code. I'm going to delete that. I'm going to reuse this algorithm, but change it. And again, I'm going to change this to return a Boolean. In this case, I don't care about the height, the size. All I care about is the result from basically my leaves or branches or whatever. Okay, left is bst equals, sorry, these should default to true. So mutable left is bst, and then mutable right is bst equals true. And then I just say left is bst equals this guy here. Change this function name, change that. Delete this. Right is bst. Okay, and then the return value is just left is bst and right is bst. So as long as both of these are true, then we're good. Okay. This is not done. Still a work in progress. I haven't actually put the check in. Okay. So where I need to do this differently is I need to say I basically need to have a check that I need to have this a check where, like this, if basically if the data on the left is not less than the data on the right, fail, basically bail out here, right? Let's do this. If left dot borrow dot data is greater than or equal to this node, like that, return false. That's it. And then on the right, it is basically the same thing, but reversed. So if the right is less than that, return false. Cargo test. Oh yeah, there's no height. Delete. This is still going to be true. Height, delete. there we go, that passes. But let me change this so that this one is imbalanced. And I'll do that by saying let mutable node equals that. So there's a node here, and I'm just going to like totally mess this up by saying node, and then I'm gonna put a new node in here with just bogus data. Let me copy. This is how a node is constructed. Yeah. This is bogus data. Boom. Oh, let me change the value to be 901. Sure, whatever. Node. What did I do wrong? Did something wrong. Oh, this needs to be a mutable reference. Boom. Done. Oh, no, this is wrong. This should be returning false. Okay, this is not right. It's definitely wrong. Insert at. Oh, there we go. I think it just didn't say it. No. That should be. It should be returning false. Oh. Actually, no. The default should be true. What is going on here? This should definitely fail, because my tree is just totally, should be totally junk here. Oh, you know what? Insert at. That's right, insert at, it does the right thing. Okay, this is not gonna work. I need to like, basically like create my own insert here. So let me do this and say, yeah, basically I'm going to force my node here. Like that. There we go. Okay. Did it. So I'm basically forcing, I'm just like putting this 901, which is bigger than every other value on the left. Which is not valid. There we are. Remove this mutable. Done. That is problem 5. Right? Problem 5? Validate BST. Done. Problem 5. Push that up to GitHub. My last, I would have had a build failure in here somewhere, but this one should pass. Check back on it in a minute. All right, moving on. We're going quick today. Let's see, the next problem is, it's called Successor. Okay. Problem 4.6. Successor. Write an algorithm to find the next node in other words, the in-order successor of a given node in a binary search tree. You may assume that each node has a link to its parent. Okay, so this is a little bit trickier, or a little bit tricky, I think. Write an algorithm to find the next node in order successor. Got it. This is tricky because in a binary search tree, the order of the nodes in the tree is not necessarily related to the order of the data. Like a binary search tree is not ordered, I guess, or can be not ordered. So if you wanted to print out, for example, if you wanted to print out a binary search tree in order, doing that is not straightforward. I gotta think about this for a minute. Okay, copy problem 5. That will now be problem 6. That is the problem we are on. Write an algorithm to find the next node in order successor of a given node in a binary search tree. So I think that the way to do this is to implement a breadth first search, I believe. Okay, because the only thing that a binary search tree can guarantee is that a node on the left is less than any nodes to the right of that node's parent. Which means if you traverse the tree all the way to the left and you hit the end of the tree, then you know that that's the smallest possible value in order. And so once you've done that, if you then unwrap the tree in the right order, then yeah, everything will come out in the correct order. So actually, no, this is a depth first search. I made a mistake there. So, all right, that's pretty simple. Let's see. I actually implemented a depth first search, I think, in the first problem, right? Yeah. All right, let me copy this one. Let me delete this file. Let me copy the first one, copy, paste, and then I'm going to use the DFS from this. Oh, you know what I have to do? I have to also let me undo that. I'm gonna copy problem 5, and then I'm just gonna use the DFS from problem 1 and just like implement that in problem 6 here. Okay. So, all right, copy DFS from, just gonna delete these. I need to change these names from vertex to node because I changed that. Node ref. like that. That's basically the same. DFS from, oh, except that there are no edges here. So, okay, change this to vertex. This is gonna be left and right. Go back, I'm gonna copy, not that one. Yeah, I'm gonna copy this. So it's gonna be like, if there's left, do whatever. If there's right, do whatever else. Okay. So the order is going to be left, call the left function first, then the right, sorry, right last, then call left, then call this node, and then right. So I need to recurse before doing that. So here we go, F, and then left.clone, like that, and then right. I believe that'll do it. Let's see if that compiles. Cargo test. Nope. Oh yeah, this function doesn't exist anymore. I think I implemented an iterator before as well. I'm gonna bring back that iterator because it'll be super handy. Semicolon. I'm so used to using languages that don't have semicolons that I just don't write them anymore. It would be nice if VS Code could get with the program and just add the semicolons in for me. That would be very deluxe. Why are you failing? What am I missing here? Oh, it needs to return. That's right. I'm returning a Boolean, but I don't care about that right now, so I'm not going to return anything. Change this, change this. Yeah. Don't care about the return value. There we go. Have some warnings. Others never used, never used. That's fine. I haven't used it yet. Let me go and copy the iterator. I thought I implemented an iterator. Maybe I didn't. Oh, maybe I just thought about doing it and didn't do it, or maybe I did it and gave up. I don't know. I don't remember. What languages do I use the most? That's a good question. These days, it varies. I find myself using Python a lot, mostly because even though I actually kind of loathe working with Python, I think it's really not a good language. I use it a lot just because there seem to be Python bindings and libraries for like pretty much everything. So if I don't want to have to spend a lot of time writing code, I will use Python because I can just pull in whatever library I need. So that's probably the one I use the most these days. In terms of like day job stuff, I don't know, we use a variety of things. We use Go some places. We use Ruby. I mean, our like main product is a Ruby on Rails app, so that's all Ruby. We have a bunch of other stuff that's written in Java, like all of our like data processing related stuff is written in Java. We use Kafka a lot. We have a bunch of very large Kafka clusters. We have a pretty significant Kafka infrastructure. Yeah, Python, I don't know, you know, like when I was like still kind of learning how to write software, just like, you know, when I was like, I don't know, 16 or 17 years old, Python was a great language to me then, because it felt like an easy to use, easy to learn language. I think it was pretty good for learning programming, but it's just not really a well-designed language. It's a really poorly designed language. As far as scripting languages goes, it's like one of the least pleasant to work with. Ruby, on the other hand, Ruby is a really nice language to work with. It's terribly slow, relatively. And Python is slow too, but Ruby's even slower than Python. And I don't know, recently I haven't really found many opportunities to use Ruby. The thing I like use the most in Python library-wise is the scientific stuff, like NumPy, pandas, all of that, like that whole ecosystem of libraries. Unfortunately, there's just like nothing else, and those are the things that keep me coming back to Python. If you want to do any kind of data science stuff, there's really just nothing that beats Python, just given the you know, the depth and the breadth of all the scientific libraries and so on. So yeah, I mean, I guess like languages like R are probably better, and Julia, I guess. I haven't used Julia, but like people rave about that. Julia Lang. This is like the hot thing in data science. I've never used Julia, but anyway, if you're doing like pure Python, or if you're doing pure data science, then like languages like Julia or R make a lot of sense. But like the kind of stuff that I do, at least in like a day job scenario, tends to be like semi-data science-y, right? Like I'm trying to like munge some data into something else, you know, like read in a CSV and spit out something else, that kind of stuff. That's like, you know, that's like 98% of like day job work right there, in my experience at least. So for that, Python, honestly, I think can't be beat, mostly because of the libraries. Although if you're like optimizing for performance or whatever, then again, like Python's probably not the way to go. Okay, I've got a DFS. So if I run this DFS, it should print out my, and I just print, it should print out. Actually, I just realized I basically already got this implemented here. Maybe, no, okay. Oh, I actually, yeah, no, this is done. All right, let's call my DFS. In theory, if I did this right, it should print everything out in order. So I'm gonna use an iterator here. And I'm going to say, or I'm going to call my my DFS, and then node, and I'll just say assert equals Oh, actually, I need to iterate my iterator before I do this assert. And I want to say let value equal iter.next, and then value, this should be equal to whatever this guy is. Oh, sorry, it should be assert equals like that. Oh. Oh, I'm borrowing the wrong thing. Sorry, this should be node, not value. I should unwrap that as well. Right? Expected type, found type. Change that to a reference. There we go. Something's not right. Left, right. So, yeah, one thing interesting going on in the Rust world is WASM, Web ASM. Oops, I just closed the browser. I don't do like any, generally I don't do much front end type stuff. I've written like, I've used like React and so on plenty, but not really day to day. Yeah, WebAssembly provides a way to run Rust code in people's browsers, which is pretty cool. I think the safety features of Rust really don't matter, or don't make as much sense in the context of web browsers, because everything running in web browsers is basically already sandboxed anyway. The main risk is not the code, right? But rather the browser implementation. If the browser, itself has some like buffer overflow or whatever, then you're gonna have issues. As we've seen recently, there was like a Chrome vulnerability pretty recently in the news. I don't know what the details of it were exactly, but I upgraded my browser. It's probably like use after free. I was gonna say it was either a buffer overflow or use after free. Yeah, this just came out. This is like apparently a pretty serious one. But anyway, yeah, upgrade, if you use Chrome, upgrade your browser so you don't get pwned. Does anyone say that anymore? I remember when that was like the funny thing to say. No, that was the funny meme, saying pwned, like P-W-N-E-D or D, pwned. And then like there were variations of it, like pwned with a T instead of a D or whatever. Anyway, let's figure out why my algorithm is broken. Cargo test. Why is this not right? So it's blowing up. Left is 1 and right is 2. Oh, wait, no. Huh. Am I calling these out of order? So I'm calling left first. And I'm calling this node. And I'm calling right. So left. So left should only get called if left. Oh, I see. It's because I'm double calling these. So I should never be calling this here. I just realized, because if this node exists, it's going to call that function. Yeah. Okay. Dir. Okay. There we go. That should be it. Boom. Done. That's problem 6. Oh yeah, I need to call this DFS down here so that the warnings go away. I just print it out or something. Print. Too many exclamation points. Oh. Wrong name. Cargo format. There we go. Problem 6. Done. Never had an interview that had them do coding problems on the spot. That's unusual. I think, well, with like a couple of exceptions, there's like, I guess there have been cases where I've interviewed at places where they were satisfied with my just like looking at some of my open source stuff. And they didn't make me write code, but that's definitely been the exception. I have almost always had to do these kinds of problems in interviews. All right, what is the next problem? The next problem is called build order. So that sounds like a variation on the problem we just did, which was about the ordering. Okay. Build order. It says you are given a list of projects and a list of dependencies, which is a list of pairs of projects, where the second project is a dependent of the first project. All of the project's dependencies must be built before the project is. Find a build order that will allow the projects to be built. If there is no valid build order, return an error. All right, so this is like a basic DAG problem. And it looks like I'm guessing the solution here is DFS again. So this is different from binary search in that in a DAG there isn't necessarily any ordering. So I'm going to go back to problem 1, which was a DAG, and I'm going to copy that. DAG, by the way, DAG, that's a directed acyclic graph, which is just a type of graph. Now what did it say? In the book, yeah, in the book it's, let's see, but it's describing dependencies as A depends on D A list of projects and a list. Okay, so it says a list of pairs of projects, where the second project is dependent on the first project. Yada yada. Okay. It doesn't necessarily say anything about how many dependencies or whatever, but this will be fine. I can reuse problem 1. So what is this one called again? Build order. So let me just construct the graph that is in the book, in the problem. And it is, so the projects are A, B, C, D, E, F. Let's make those A. B, C, D, E, F. Right? A, B, C, D, E, F. All right, and list of pairs where the second project is dependent on the first project. So the first dependency is A and D. So D depends on A. Okay, D depends on A, like that. That'll be a.clone. Okay, and then the next dependency is F depends on B. Be b.clone here to find that dependency. Oh, this is wrong. Hold on. A, B, C, D, E, F, like that. And then B depends on D. Okay, B depends on D. Though D doesn't exist at this point, so these have to be reordered like that. B depends on D. F depends on A. Which is here. F depends on A, like that. And D depends on C. Okay. D depends on C. Is that right? A depends on... Oh, I just messed this up. Oh, I messed this up. Whoops. This is wrong. Okay. A depends on F. Like that. C depends on D. Is this right? Hold on. D depends on A. D depends on A, got that. B depends on F. B depends on... What did I do here? Yeah, I messed this up. B depends on F. And then D depends on B. Okay. Did I mess this up? A depends on F. Yeah, I have that. And C depends on D. I have that. Okay. E is just out there. Is that right that D depends on both A and B? D, A, and B, yes. Okay. F depends on A. No, that is wrong. F does not depend on A. It's the other way around. There we go. I think that is right. Cargo test. Delete these. D doesn't exist there, needs to be moved down. There we go. Okay. So here in my graph, so I think there's one thing I did not implement properly in this graph, which is that if a vertex has no parents, it just kind of disappears. So I need to change this from an option like this to a vector, and then say, and then I would say, instead of doing this, it would be head push, like that. Right, so head is a list or a vector. Okay, and then here, similar. Like that. Oh yeah, this should just be an empty vector like this. Expected RC found option. Oh, I guess this is yeah, just an RC, not an option anymore. Okay, there we go. So that compiles. It's not done. I need to do the search again. I'm gonna delete this has path. Don't need that. I'm gonna copy the DFS from the previous problem, because that is the I'm doing the same search over here, basically like an ordered search, and change node ref to vertex ref. Vertex. Oh, this algorithm changes. This algorithm is going to be like, the DFS is going to be like it was in the first problem. That's right. Okay. Oh yeah. Let me delete this stuff down here. I have too many DFSs. Okay, so the order in which this stuff happens. So this is reversed, right? So first, I would build the top level thing, and then I would go through here, like this. Yes. Okay. Semicolon. This doesn't need to return anything. No return value. Just like that. Get rid of the turn value, return value. Just like that. Cargo test has path. Do not want. Copy this into main here. Cargo test. Oh, change the type. This does not need a return value. There we go. Okay, I need to actually write the test because that's not happening yet. So here I'll have a vector, mutable vector, order, call this graph order. Okay, and then I'll just do a DFS. Say graph.dfs, vertex, and then graph order dot push the vertex value like that. Okay, that runs, and then I will say assert equal. The order of this should be so it should be F A B D C E. It might be slightly different ordering, but like E can happen at any time and F can happen at any time, but as long as, yeah, let me run this and then check. Left. What happened? Left, right. Why do I have a, yeah, okay. That is an error. What am I doing wrong here? So I'm seeing D twice because there are multiple dependencies on D. Although the order I think is right. It's just that I have D and C. Why do I have C twice? Presumably because I have D twice. Just gonna look in the book and see what it says for the order. Should be F, E, A, B, D, C. Yeah, E can be last. That is fine. But let's do it. Yeah, let's just make it do what the book says. I see. So it's because of this order. If I add E before F, sorry, after F, no, that's not gonna make a difference. I'll just leave it. It doesn't matter if it comes out last. But I do need to get rid of the extra D's here. Okay, so the add vertex parent vertices. Yeah, basically I'm visiting D multiple times, so probably the easiest thing to do here is to just check if I have already got this node. Basically implement a poor man's set. Contains say value equal vertex data, sorry, vertex borrow data. Okay, so if this value is not already in there, add it, otherwise do nothing. This should be a reference. The order is still not the same. Let me check if it's actually wrong or not. So left is FAD CBE. What's the book say? FABD ABD B should come before D. Is that right? Do I have these dependencies right? I think I have it backwards. D depends on B. D, yeah, that's right. And B depends on F. C depends on D. And D depends on A. Where is it breaking down here? Yeah, okay. D should not be printing before P. So, I'm missing something here. What is it? DFS from where am I messing it up? For parent in parent versus parent edges push. Oh, looks fine. So if there's no parents, basically nothing depends on this vertex, then yeah, that just goes to the head. Okay, and then if there are dependencies, then add this node as an edge on that parent. That's right. Okay. So where does it break down? I'm printing out FAD D. So D has two parents, A and B. Okay, I think I understand where I messed up. So the problem, I think I flipped this around the wrong way. Yeah. No. Yeah, no, that, oh, no, that's backwards. That's not right. What am I doing wrong here? So my dependency relationship is that for each node, specify the parent. Yeah, okay. And the parent says, parent relationship means all of the I think I've done this wrong. Yeah, like reversed it. I think I should be adding the actually, I don't think it makes a difference. Whether you specify the parent or the child shouldn't make any difference. But obviously my algorithm's wrong. For parent in parent vertices. So if a node has no parents, that means nothing depends on it. I should really do this the other way around. I think the way I've done this is like basically backwards. It doesn't make sense. So I'm going to flip these around. I'm gonna flip the algorithm around, basically invert it, right? So rather than defining the dependencies as parents, I want to define the dependencies as children. So this should be a.clone, b.clone, like this. And then A and B. So D depends on A, yeah. So d.clone, and then depends on B, d.clone. So it should really be like this. It's a relationship between C and D. C depends on D. This should be the other way around. It should be c.clone, like that. I have to move these up. Right? My brain's getting confused right now. What did I just do? A needs to exist. There we go. Okay, and now I need to change the order of this. Sweet. Is almost correct. Very close to correct. Just A and B are switched around. Just fine. Just reorder them like that. Boom, done. Okay. Kind of did it like the inverse way the first time around of the right way to do it, and I confused myself. But we're done now, I believe. Let's check Clippy. Oh, Clippy's not happy. I gotta let me just copy this code into main so that Clippy is happy. No, Clippy's not happy. Come on, Clippy, be happy. Clippy does not like having one character variable names. I can't blame it. How do I make Clippy happy? Let's just append underscore vertex. Whatever. Like that. Yep. Yeah, I'm letting Clippy be the boss here. Most of the time, Clippy is quite helpful. So I choose to let Clippy be in charge, rather than having my brain do the heavy lifting. Get status. All right. It's problem 7. Let's take a look at the next problem. Problem 8. It's called first common ancestor. Right here. Design an algorithm and write code to find the first common ancestor of 2 nodes in a binary tree. Avoid storing additional nodes in a data structure. Note, this is not necessarily a binary search tree. First common ancestor. Okay. First common ancestor. So I think this is another, well, this is another graph search problem. And I think it's pretty similar to the one I just did here. So let's copy that, call that problem 8. First common ancestor. So a common ancestor is a vertex in the graph where the basically like where two paths or whatever in that graph meet. So in order to finding a common ancestor is simply a matter of doing a search and then finding the left and the right nodes, and then returning the node where both the left and the right, or not the left and the right, but where basically there are two there are results from two nodes. Yeah, okay, that makes sense. Okay, I'm gonna reuse this same graph here. Let me just leave all that code in, but I'm gonna rename. I'm gonna leave the DFS in, but I'm gonna add a new search, and I'm gonna say just call it common ancestor from, and common ancestor. Okay, and so the common ancestor search is going to take in, it's going to take in a function, and it's going to take in two vertexes. Copy this. I can call them left vertex and right vertex. They don't actually have to be on the left or the right, it doesn't matter, but I'll do that anyway. Okay, call those, and then append that there. And yeah, so I would search. I can make this return a Boolean because, sorry, bool, because I want to stop searching as soon as I find what I'm looking for. Run cargo format. Common ancestor from left vertex, right vertex. And these can just be references like that. Left vertex, reference, reference. Okay, and then I'll just say if common ancestor from whatever, return. And if it's never called, then whatever, don't care. Okay, and then here, common ancestor from basically what I would do is I would call this function on this vertex if I get two results. Really simple. So I can actually just use a Boolean here, mutable bool found 1 equals false. Okay, so when I find 1, all I need to do at that point is find another. So I'd say if common ancestor from blah blah blah, if that and I found 1, then I'd say call this function and then return true. That's it. End. Okay. Otherwise, or actually, let's change this slightly. Like that. Okay, so if I found a common ancestor and I found 1, then do that. Otherwise, just mark this as having found 1. Cool. Code's messed up here. What have I messed up? Started to warm up here in New York, so air conditioning has started switching on. Now I'm freezing. Forgot how flippin' cold the AC is. Ugh, I should put on a sweater. Okay. Common ancestor from why is my code not working? Not compiling. Unclose delimiter. Oh, there we go. Expected 1 of. Oh, that's not valid code. There we go. Okay, now I can read it. So for each edge, repeat this algorithm. Okay. And then here, I'm going to return RC pointer equals, and the pointer here is going to be, yeah, this vertex. And either one of these, either the left vertex or the right vertex. This isn't going to compile, but I'm just writing it out here in a moment. Fix it in a moment. Turn true, turn. Wait a minute, I'm doing this wrong. Sorry. So I'm searching, I'm doing the search wrong. So it's more, I've got a list of edges. So I'm looking for 2 matches. And I can't do it with like this with one recursive function. I'm going to simplify this a little bit. I'm going to say yeah, so So this recursion should happen at essentially at a different depth. So I'm going to search first, and then say if pointer equals left vertex or this vertex, yeah, or right vertex. Okay, this makes more sense. So if either one of these match, yada yada, do that, and then at the end here I would say, then I would do the recursion, basically, because that's when I would go an additional depth in. Okay, this makes more sense. Yeah, and as soon as I find 2 pointers that are equal, call this. Because that means that no, this still doesn't work. I have to do this differently. I think this common ancestor from function needs to return. Does it no, actually returning Boolean's fine, because as soon as I'm calling this function with the ancestor. I'm calling f here with the ancestor. I only care about the ancestor. I don't actually care about these guys or where they are. Yeah, it doesn't matter. Okay. I think I'm on the right track. And then here, this is the point where recurse. So if I get here and I haven't found what I'm looking for, then I do the recursion. Yes. I believe like that. Should be a return. Basically the case where there's no more is false. Cool. Okay. That compiles. Let's try and construct a test here. Okay. I'm just going to reuse the same data, and let's call this common ancestor. Graph common ancestor, and the common ancestor for let's see, for common ancestor for A and B should be, let me reorder the function arguments. I want to make the function the last argument here. to make it look a little better. Make the code look better. Okay. Common ancestor, so this should be go A vertex, B vertex. I need to clone these. And the common ancestor should be RC pointer equal, should be vertex and D. Okay, I don't think this is going to compile, but assert pointer equal true. What? Did that work? Let me just add another was called equals false. I want to make sure this is actually being called. Let's call this, let's do what's called equals true, and then assert equals was called true. Dang, all right, did it. It works. I just copy the test code into main here to make sure all my code's running. Clean that up. Let's see what Clippy has to say. Graph order, do not care. Do not care. Cargo Clippy. This loop never actually loops. Well, that's strange. Clearly I have done a thing wrong somewhere. What? This loop never actually loops. Why is that? Why is that? Are you sure about that? Because that shouldn't happen. I'm confused why that is. This loop never actually loops. Oh, it's because it... Yeah, okay, this is wrong. I should be doing this. There we go. There we go. Test shouldn't have passed, but they did, so whatever. Now we're good. Thank you, Clippy, for helping me find that bug. I would not have caught that. The code would have been wrong if not for Clippy. Thank you, Clippy. You're doing fine work, little buddy. All right, let's push that up. I'm gonna take a little break here. A little 5-10 minute break. I will be back in a flash. Gonna maybe get a little snack, have a bio break. I'll be back. I'm back. Chewing with some nuts that I was just eating. Delicious nuts, salty nuts. We just finished problem 8. Next problem is problem 9. Go figure. There are only 4 problems remaining in this chapter. I guess I've done 4 problems today. Try to do 1 or 2 more. I don't know, maybe I'll finish the chapter off. I'm looking ahead at these problems. They don't look that tricky. So, yeah. Some of them are a little tricky, I guess. There's one here that's interesting. Random node. Doesn't really say anything about how it should be implemented. What else? Paths with sum. You are given a binary tree in which each node contains an integer value. Design an algorithm to count the number of paths that sum to a given value. Interesting. All right. Excuse me. The next problem is called Bst sequences. Right here. Problem 9. 4.9, chapter 4, problem 9. Bst sequences. It says, a binary search tree was created by traversing through an array from left to right and inserting each element. Given a binary search tree with distinct elements, print all possible arrays that could have led to this tree. Print all possible arrays that could have led to this tree. Interesting. Two on 3, 2, 3, 1. I have to think about this. This one's kind of tricky. Interesting. Maybe it's not tricky. It may just seem tricky, and I think like that's kind of the nature of these problems. Let me just monologue for a bit here. I was just thinking about this, how I think one of the reasons why these problems are bad is that while it tests your ability to kind of solve problems on the spot, if you're doing these like in interview context, it definitely tests your algorithmic knowledge. Knowledge is not the right word. It's not so much knowledge of algorithms, like have you memorized every algorithm? It's not that. It is more of your ability to, well, it is that actually. Take back. If you already know all the algorithms, then it's pretty relatively easy. What makes it easier is knowing all the algorithms and knowing how to actually apply them to the problems, I guess. There's like a subtle distinction there, right? Like knowing about a DFS, knowing like I have to do a search. Is it a breadth first or depth first? And how to implement those. And then actually being able to like draw the connection between the algorithm and the problem, the way it's asked, right? That's what makes it tricky, right? And the trick is in that the problems are not posed in the way of like saying like implement a depth first search. The problem is posed by saying like here is this blah blah blah, and now you have to figure out on your own that you have to do a depth first search, and so on, right? That's what makes them tricky. But I think generally this, like these like cracking the coding interview style problems are bad, even though certainly once upon a time I thought these were good problems, but nowadays I think they're bad because in addition to not really representing what most people do day to day in a software job, which is like lots of meetings and arguing with people and stuff. Just kidding. You know, in terms of like writing code, it's more, I think like my opinion is that writing software is more about style than a lot of other things, right? In fact, like I was having this conversation with people at work. Someone asked me like, the question was, is software more like math or like writing? And I think once upon a time I would have said software is more about math. It is about the calculations and getting the right answers and so on. However, nowadays I feel differently, and I think that software is more about style. I mean, like writing good software is more about style. I think style matters more, provided, you know, things are correct. Correctness is very important, of course, but style is very important because when it comes to software, I think art is the right word. When it comes to software, the most valuable code, the most valuable software is software that other people can use and understand and pick up and contribute to. When someone just like comes along and just dumps a bunch of really cryptic code, frankly, unless it's doing something like very small and specific, then, you know, it's not that valuable in my opinion. Hello, Dan. Welcome. Yeah, I often joke when, or not joke, I mean, like, I guess I'm like kind of serious. I often say like I think of myself as more of an artist, and I think of like writing software as my craft, and I try, you know, I guess like my goal when it comes to writing software is to write software that doesn't need comments. It should be code that describes itself and is something that someone else can come along and pick up and look at and be like, oh yeah, I know exactly what's going on here. I know how to make this better. I know how to change things and so on. I think that is the best kind of code to write, is code that is easy for someone else to understand. Yeah, exactly. Do complicated things and make them look easy. I'm not saying that I'm good at that. In fact, like, I only feel like now, you know, having been, you know, I've like been writing software for like 20 plus years. Professionally, I've been doing it for well over 10 years. And I feel like at this point, I'm only kind of just beginning to really understand how to make good software. And I've gone through like various phases, I would say. Now I'm at the phase where I dislike complexity generally. Even though, like, you know, when I was younger, I thought like, oh, complexity is good because it makes you look smart or whatever. Like, I wrote this really complicated thing, so people are going to be impressed by me, and so on. Now I think the opposite. If it's something that I like can't really understand easily, if it's something that like takes me a really long time like thinking about to really understand, then I have a natural aversion to it, whatever it is. So anyway, so talking about interviews and interviewing problems, my preference regarding interview problems, like if I was deciding what the interview problems were, I would focus more on practical problems, right? So like an example of a good practical problem would be, you know, ask somebody to like build a REST service, an API service that does something. On like the more like front end, like React side, I would say like, you know, build me a simple to-do app or whatever. The to-do app thing is, you know, like if you've done any React, you've probably seen the to-do app thing 1,000 different ways, but actually sitting down and writing it, it's not that hard. It wouldn't need to be like a complete implementation, something you can do in the span of like 2 to 4 hours. And the things that are interesting to me are just like, what does the code looks like? Like, what is the style of the code? How do you name variables? Can I understand what the F you're doing? You know, did you build this code in such a way that it's, you know, it's just like stylistically good, I guess. But anyway, I really don't like the 30-minute to 1 hour coding interviews, the type of which you find in this book. I think they're bad. I think they're also going out of fashion right now. I think they've lost popularity, which is good, even though I think most companies are still doing these, you know, like Google and Facebook and all those big companies, they still do this shit, but it is going out of style, thankfully. I think that's good. And yeah, anyway. Yeah, take-home projects also have like a different issue, like you mentioned. I think like the issue with take-home projects is like, I think interviews should be on site, and I think interviews should happen usually paired with someone, right? On a computer, right? Like if I'm writing code, I should be writing a code on the computer, generally, because nobody really writes code on a whiteboard like day to day. I mean, maybe occasionally you might like write out some pseudocode in a meeting or something, but it's not really it's not really a thing that happens. Yeah, and Stack Overflow. So like that's another thing. I think that in on-site interviews, people should have complete access to the internet. I think people should have access to Stack Overflow, and I think if you try to get through a problem without using Stack Overflow or like reading documentation, I would consider that a signal, right? Like one thing that is really important is whether or not people have the skills to solve their own problems. And it is especially true in programming that like people who do a good job tend to be people that know how to find answers themselves, and like can do things asynchronously, right? If you depend on 10 people to get anything done, then you know that you basically are doing everything synchronously. You should be able to unblock yourself. All right. Enough about that. Let's do this. Let's try to figure this out. So BST sequences. Binary search tree is created by traversing through an array from left to right and inserting each element. Given a binary search tree with distinct elements, print all possible arrays that could have led to this tree. So I think I understand this, maybe. All possible arrays that could have led to this tree. So this problem has to do with the fact that so if you have a binary search tree, there's a big difference between a binary search tree that is balanced and not balanced, right? Like an extreme case of an unbalanced binary search tree is one where it looks like a linked list. You just have like a node, and like you know, it's like a list basically. It really isn't a tree. All nodes in the tree are basically to the same side of each other through the tree, right? That would be an extremely unbalanced binary search tree. So in that case, it's really easy to figure out how the tree was constructed. So determining how the tree was constructed from the tree itself is not impossible, but basically you only have two possible options, right? Like for each node, right? So I think what this is getting at is that for each node in a tree, there are two possible ways to have constructed the children nodes, right? Like whatever the head node is, the root node is of a binary search tree, that node had to be inserted first, and then for the two like child nodes, left and right, those could have been inserted in either order. It doesn't matter. All you know is that the root node was inserted first, right? Had to be inserted first, which makes sense. That's exactly what in the problem here. That's exactly what's written out, right? Focus, please. Focus. Stupid camera. Anyway, so like right there, very simple tree. You have 1, 2, 3. 2 is the head node, or root node, whatever you want to call it. Please focus, camera. Focusing is just like super unreliable. Well, whatever. And then the output, it's blurry, but it says 2, 1, 3, or 2, 3, 1. So for essentially for every node that has children, you have two possible arrays that could have constructed it additionally, if that makes sense. Yeah. Okay. So I think I understand how to do this. Yeah. Of course, it's another search problem, obviously. What problem is this? This is problem number 9. BST sequences. So 8 was the last one we did. Let's paste this. Actually, let me delete this. I'm going to copy one of the last BST ones because these last couple problems were DAGs or graphs, which, I mean, it's not really that different from binary tree, but it is subtly different. So let me start from problem 5 here, which was the last binary tree one. There we go. Oops, forgot to switch my screen. Switch that. Haven't missed anything. I've just been copying the file. There we go. So add that. Let me restart VS Code. It seems to have shit the bed, as they say. It happens, unfortunately, quite often, especially with the Vim extension. I use the Vim key bindings extension in Visual Studio Code, which is like, it's pretty okay. It's not amazing, but it's good enough. It's not as good as like native Vim, but I'll take it. Okay. BST sequence. Test, check, or what are we calling this? Test, get, BST sequences. Let's call it that. Paste this up here, save that. Check is BST. Just gonna delete that. I'm gonna delete this. I'll leave in this add vector. That's a handy function. Let's see if this compiles. It does. Oops, I closed the wrong window. Open that again. All right. Okay, so of course the easiest way to implement this is with recursion, and yeah, let's do it. So let's call this get BST sequences. So taking a self, and it's going to return a vector of vectors of type T, like that. Let's test that. Yeah, that's fine. Return an empty vector to make the compiler happy. We are good. We're good. We're doing it. Okay. So, what is this algorithm going to do? There's going to need to be an inner search here. I'm just going to call this inner. Can return the same thing. There we go. And then this will just start from the head node. The search here. So this is similar to a problem I did before, where you have to essentially like roll up the results. I don't remember which one that is, but I'm just going to do it again from scratch. And pop these on. Have some music. Okay, get BST sequences inner. This can just take in a node ref. Node ref of type T. And then here I'll say if let sum head equals self.head. Just be regular equals self.head. Else turn empty vector. So here this is just going to return get BST sequences inner self.that. With the head.clone, no semicolon. This should be head as ref with no unwrap, like that, I think. Wait, head is an option. Yeah, should be like that. Right? Where's head? Head is an option. Option to a node ref. There we go. Okay. We are good. So the sequences to create this guy is just going to be should be mutable. So it's just going to be a vector with just this node, basically. Should be, sorry, borrow data. There we go. Okay, so here, so I need to do the the zip, the roll up of the results. And yeah, I'll do that here. Also, so I'll basically say if let some left equals node dot left okay. All right, so if there's a left, and then if there's also a right, this is basically going to be duplicated here. Because there are like four states, well, 3 states, where you have a left and a right, where you have a left or a right, or you don't have either, right? So it's gonna look like this. So the sequence is basically, so if you have a left and a right, I gotta get the sequences for both left and right. So left sequence equals self.get bst inner for left, and then right sequence like that. Whoops. And then Here I will return a vector with a sequence. Let's look up the Rust vector documentation. Basically, I want to get a new vector with a value appended. Like I want like an immutable append. Rust vec immutable append. Is that a thing? Concatenate two vectors. Yes, this is what I want, but I don't want to use append. Moves all elements of other into self. Can I just clone it? There should be a clone. Yeah, I'm just going to do that. Sequence.clone.extend left. So I'm going to take that, extend it with the left sequence, and then do the same thing with the right. Like that. Yeah. What am I doing wrong here? This doesn't need to be mutable also. Mismatch types. What is extend return? I think I should just use append. Okay, I don't think I can do that because of how this works. What does I want these to like return a new vector. What does extend return? Where is the extend? Extend. Why can I not find the extend documentation? Extend. Vec. I see. Okay. Extend is a function on an iterator. I get it. So clone returns a new, but the problem is that append does not return the array with a vector. There's elements of other and self thing, other empty. This would be really convenient if that returned a vector. Yeah? wouldn't it? All right, whatever. I'll just do this. I'll just make these mutable and then do it in place. So like this. I don't know, that's not going to do what I want. I need to do... Oh, this is annoying. There's just like no... There isn't really a clean way to do this. I want to make a copy of this sequence here, which is like the default, and then I just want to append everything left over to that sequence. Alright, whatever. I will do this the verbose way, which is kind of ugly, but it'll work fine. Call it left final sequence. Equals this guy, and then oh, you know what? I'll just do it like this. This is actually not bad. Okay, like this. Dot append. There we go. That's not bad. It's kind of verbose, but I'll take it. Right sequence dot append. Yeah, like that. Oh wait, this doesn't make sense. I can't do this because this returns a vector of vectors. Yeah, that's right. So this actually needs to be a zip. Or zip-like thing. Let's just do that. Okay, let me undo what I just did. Go back like this. Just comment out the return statement here. So let's deal with the left sequence first. So let's do a zip. No, zip is not what I want. Basically, each one of these recursive calls could return n different, up to n different arrays. And for each n, I need to essentially double the possible it's going to double the number of different arrays that could have constructed that sequence. Yeah. So I need to construct all possible sequences for the left and for the right. Okay. I may be thinking about this too hard right now. May have been in the code too long. right? So at the very bottom, at the very bottom of the tree, there's only one possible sequence, right, for that node. And that is just whatever that node is. Yeah, okay. Then for the case where you have a left and a right, there's only two different sequences that could have constructed that combination. That's basically the head plus the left and the right, and then head plus left and the right in the opposite direction. Or in the opposite order. Got it. Okay. I think I'm thinking too hard about this. It should, I think the number of options should double. It should be like, yeah. This should be like 2 to the n. 2 to the n? Yeah, 2 to the n. So I think it should be like this. And then I do a map. And then for each array in here, yeah, okay. This makes more sense. I am going to basically take this. Sorry, take this sequence. So I'll just call it inner sequence equal sequence.clone, and then inner sequence append I'll call this child sequence. There we go. This is what I want. Should be an iterator, iter map. There we go. Copy that. This should be immutable iter mute. Right? Yeah. Okay. And then this is the same, but right instead of left. I believe. we need to call collect on this. Collection cannot be built from, why not? Why does that not work? Do I need to define that this is a vector of type T? Probably. Oh, it's probably because this is actually, yeah, that's right. These are like that. This needs to be mutable. There we go. Okay. And then here, I'm just returning a combination of these. So I can just say, I can just say, just make one of these mutable. Doesn't matter which one. Then I just say, actually I think they both need to be mutable. There we go. So I think that's doing the right thing. No, this is kind of, this code right here is kind of a, it's kind of the whole thing. So let me just pull it out. I can put this into a function. Or, well, let me leave it here for now. What would I call this? Yeah, I don't want to do it. I'll just leave it out as a separate function. I wanted to just like collect this. These things are basically doing the exact same thing. It's kind of ugly to have it all repeated. Let's not do that. So this I can pull up though. Put it up here. Okay. And then here I would say return Code's going to be the same, like that. But without this, this is going to be right. See, this whole block right here is repeated. It's basically the exact same thing. Well, alright, that compiles. Got it to compile. There's only self left. Yeah, okay, I can just pull this out. This is pretty easy to pull out. Let's call this combine sequence. Self node node ref type T. This can be a reference. And then the sequence. I know the compiler's going to complain about this, but I'm just going to leave it right now. This function is never called. Oh, I see. The inner. This expects that, but I can just change this to a ref. There we go. That'll be cleaner too. Cool. Combine sequence. So this will be self.combine sequence. Node. I messed that up. Copy, paste, fill. Okay. Here I can actually just say return that. Here I can shorten this. I can shorten this. There we go. That is looking tidier. think this can just be as ref, like that, right? These need to be refs. This should be a reference. Whoops, I have like one too many levels. Expected struct. I see. This should be a reference. So because I'm doing this wrong. Oh, derp. That's why. Wrote the code wrong. There we go. That. There it is. There we go. Okay. That is looking better. So in theory, if I did this correctly, it should work. Let's make a binary tree. Binary tree insert 2, 2, 1, 3. Okay. Let sequences equal binary tree dot get bst sequences. Assert equal sequences. Okay, this should be like this. This should be 2, 1, 3, like that, and then 2, 3, 1. Oh, messed it up. I'm returning 2, 1, and 2, 3. Yeah, I'm combining these wrong. So, yes. There's some duplication that needs to happen that I'm not doing. In the order here. Yes. Okay. I have a lot of pocket lint. Okay, lint it to the trash. Where am I failing? Okay, so combine sequence. It's gonna iterate into here. It basically takes all the children's sequences and then effectively it's prepending the like one level up to all the children in here. Problem happens when there's both the left and the right. It's not combining these the way it should. So if there is a left and a right, I should be adding both of those. Oh, you know what? I think this is where it breaks down. I'm supposed to be returning. I'm returning vector. Right sequence, combine, left sequence, left. I'm appending the right. Some right. So I'm not combining, I think I said now, so I essentially need to combine both of them in both orders. There's two different orderings, right? So I need to do like left sequence append right, and then I need to do the right appended with the left appended. Yes. Okay, let's change this slightly. We'll call this let mutable final sequence equal empty vector of type like that. So what this actually needs is this is not, the way I did it before is not quite right. I'm like starting to lose my concentration. That means it's probably time to take a break. Let me try to finish this up, and then I'll probably call it quits for the day. Okay. Combine. I think the way that I'm doing this combining is not ideal. I kind of want to like pull it out, but starting to get rusty. Yeah, exactly. My brain is starting to stop thinking good. So if I have I have all left sequences, and once I have all right sequences, I need to take the like current value and then append with all the left and the right. Yeah. What am I missing here? My brain. I just want to throw this away and start over. That's what I'm going to do right now, because I think I have kind of lost track of what the hell I'm doing. That tends to happen sometimes. Let's just do this again from scratch. Okay, so if there's a left node dot let's just start there. Make sure that compiles. Left sequence, it's going to be this. Okay. So that is if there's a left. Let's just get this case working, which is, let's say there's a left only, then that's very simple. You had to add the first node first and then the second one. So that results in two new sequences, right? I think I'm like confusing myself by having this here. I'm gonna get rid of this like that. Or rather, let me do this. There we go. There we go. I think this makes more sense. I wonder if you can use the vec macro with a slice. Okay, doesn't matter. Stay focused here. So if I have a left, let me do the left and the right case. That is the hard one. That is the one that is confusing my brain right now. Right. Okay. So if there's a left and there is a right, then let left sequence and then let right sequence. Same thing. Like that. Okay. So here, eventually this is going to return. These are going to return arrays that look, basically two-dimensional arrays that look like this with just the one value in there. So all I need to do is take the current value and then append the left plus the right, and then the same but the other way around. Yes. Okay, mutable. Let's call this final sequence. Okay, empty vector. And then final sequence dot push, or rather, it's going to be for sequence these are plural as well, sequences, so it'll be for sequence in let me do it using a map dot iter map sequence. Okay. So for each of these, I will like both of these final sequences need to include both of these values. Yeah. So this should basically be the left and right combined. Yeah, like prepended. How do I do this in a nice way? This needs to be mutable. I'm running out of variable names. Alright, whatever, just call this vec. So the first value here should be this guy. And then it should be that. Followed by all of this other sequence. Like that. Why does it not like this? Differ immutability. Does this have to? Yeah, it does have to be immutable iterator. Oops. Intermute. Immutable. What? There we go. Okay. So then I need to basically do the exact same thing. Well, I need to combine the left and the right. So to do that, you know what? I should just do it like this. I can do an insert. Sorry. Because it's really annoying that there aren't mutable or there aren't immutable there aren't enough immutable operations on these, because like the thing that makes this tricky is that I don't want to change these in place. I just want to create a new, I just want to create a copy and do that, but I can't because of the memory stuff. It's really annoying. Okay. So I'm going to do I need to like do this here. Map. And then I want to return, I basically just want to prepend this value. So I'm just going to overload. Can I just do this? This is already mutable. I can just do insert. Let's clone it. Okay. This should be left. Sorry. I just had another thought. My brain is like, is really not doing good right now. Let's do this. I'm just gonna do it the mutable way, which I think will be much easier. So I just want to append. No, I can't do that because these are I need like an append all or something. I can't do that. I have to like iterate over every one of these. I think I'm like trying way hard to do this in a really concise way, and I'm just making more work for myself. All right, so for each of these and for each of the left sequences and each of the right sequences, All right, last sequence. Basically, I need to do this twice. Oh, this. Should be push, not append. There we go. Cool. I think it is almost right. No. Okay, now I just need to handle the other cases. Shit. I think I have like missing. There we go. Okay, this is still garbage, but getting closer. Okay. It's basically one final case that I need to handle, which is the base case. Boom. Got it. All right. Took a while. It was harder than I thought initially. Wait a minute. I did mess something up. I'm not quite sure what it is yet. Oh yes, these are reversed. Should be RL, like that. Boom! Did it! Done. Alright, that one was kind of tricky. Good status. That is it. I'm going to check that in after I run Clippy. Make sure, no, Clippy's not happy. I need to make sure this code's being tested in main. Add vector is unused. Delete that. Delete, delete, delete. Cargo test. All right, done. Problem 9. Oh, messed up my commit log. Oh no, I didn't mess it up. Push that up to GitHub. Let's make sure that actually builds. Well, I think that's it. Thank you for tuning in. I'm gonna call it a day. I gotta take my pup to the park. It's been a while. She probably has to pee. Yeah, thanks for tuning in. Thanks for everyone, Will and Jonas who stopped by. Hope you guys tune in again, and hope you enjoyed it. I'll be back probably tomorrow. I think this is gonna build fine. All right. Bye for now. See you guys next time.